resistance. What is internal resistance?
Resistance of the circuit.
Resistance of the
resistance within the circuit.
Well, it applies to a cell, so not a circuit, but a cell, battery, okay, or cell. So a battery is a number of cells connected together. So internal resistance is a property of the cell, and it arises from the materials that are made in creating the cell. So the acid, the metal plates, or the chemicals, whatever's in the battery or cell, that all adds to the internal resistance. So we represent it as a cell and a resistor in series with it. Now that doesn't mean there is a resistor in series with it. This is a property of that whole thing. And we have two things. We've got EMF and potential difference. Anybody tell me the difference between EMF and potential difference? EMF is when we're not drawing current from the battery. So EMF, what does it stand for? Electromotive force. Electromotive force. And it's when the current is zero. So we have a measuring device that can measure the voltage across the thing when we're not taking any current from it. But the potential difference is the voltage across the terminals of the battery when we're taking a current, when we're using the battery. So the potential difference is either less than or equal to, but normally less than, the EMF. Because as soon as we start taking current from that, then the resistance of everything that forms the cell or battery will reduce the voltage appearing across the terminals. So the next part is derive an expression for this. Sorry, I'm not turning that over so you can see on the board there. Here we go, number 7. Derive an expression for the internal resistance. We've got this cell. It's got an EMF of 12 volts. And we connected a 20 ohm resistor across it. There we go. 20 ohms. We'll call that R. Let's label that A, B. And EMF we'll call E. So can we say that the VAB, the voltage between A and B, is the EMF of the cell minus the voltage that's lost through the internal resistance, which we'll call I. So we're assuming a current I is flowing in the circuit then. Okay, well, can we go any further? Yes, we can, because we know that VAB equals I big R, this resistance here. So we can eliminate that, VAB, and we can say that IR equals E minus IR. And we're trying to get the internal resistance. So what are we going to have? We're going to have E minus IR equals IR. So E minus IR over I equals R, which is, leave it like that. Or if you want to do E over I minus R. Okay, and I'll leave you guys to plug in the numbers for part C. Again, you should be able to derive that expression. It's just using things that you've worked out already. All right, we just do one more of them. Number 9. Calculate the photon energy of radiation that has a wavelength of 500 nanometers. Somebody give me the equation we're going to use here.
Energy equals to Planck's constant time frequency.
Okay. Energy, photon energy equals Planck's constant times the frequency. But we don't know the frequency.
No, we can't. Find the frequency from
Yeah, which is formula velocity.
equals to n lambda, so velocity of light divided by wavelength.
Velocity is frequency times wavelength, so we put that in there. So E equals H C over lambda. I give you Planck's constant. 6.6 times 10 to the minus 31 times 3 times 10 to the 8 over whatever the wavelength is. 34. 500 nanometers. Do we have to do anything with that value? What?
Times 10 to the power minus.
Good. So 500 times 10 to the minus 9. You should be able to put that pretty well in your head. What is the other side? Should be about 3.96 times 10 to the power of minus 19 joules. I didn't check these answers, but they're probably okay. All right. What about number 10? There's a nice easy question for you. 3 capacitors connected together, 2 of them are in series, and then that combination is in parallel with this 6 microfarad capacitor at the bottom, and I want the total capacitance. So, can somebody tell me where I start?
First calculate the one in series.
Yeah, the 2 in series. So we've got a 4 microfarad capacitor in series with an 8 microfarad capacitor. How do we do series capacitance? 1 over. So 1 over C total equals, what are we going to put in here? Yeah.
4 into 10 to the power.
It's safer to do that. You could get away without doing, because if we don't, it's just going to give us the answer in microfarads anyway. So, but remember, the easy way of doing this is, do you remember the shortcut?
8 times 4 divided by
Yeah, product over sum. So the total capacitance is product over sum. So 4 8s are 32 over 12, which is 4 8 over 3, 2 2/3 microfarads. So this is equivalent to that. So now what do we have to do? One more step and we've got the answer.
just added this.
Right, because now they add together. Okay, so this combination we just add to the 6 microfarads. So altogether, 8 2/3 microfarads. Now that's the capacitance, but what about the energy stored? We've now got this circuit and we've connected it to a 20 volt supply. So the capacitors charge up, they're now storing energy, and if later on we connect them across a resistor, then they'll discharge as I showed you at the beginning. So what are we getting for the energy stored? Formula somebody. Energy. Do you have any thoughts what it might be, the formula?
QV, 20 volt times the
Yes.
total.
Yes? Okay. The one I was going to actually use was half the one I showed you which is a half CV squared, but QV is fine. How can we relate this to QV? What would we do to go back from here to show your formula, which is E? So he said that E equals QV. Well, we know that Q equals CV. So we can substitute that in. What is it? So, what about a factor of 2 actually? Well, this is the one, if you're going off the notes I've given you, that's the one.